Hi, I'm John Caparelli. Welcome back to part 2 of our structural training provided by the City of Santa Clarita. We're talking about wood frame residential construction. We're going to go ahead and pick up where we left off, and we're going to start to talk about the physics of structures, how structures behave. And us engineers, we love physics, and so we get really excited about this topic. And we're going to start getting into some of the real fun stuff. So let's go ahead and move on to beams. Like I mentioned in the first part of the training, we're not just going to talk about how. I don't want this just to be about, well, this is what the code requires and this is how you're supposed to do it. I want to talk about why. And so discussing the physics of beams is going to give you that feeling for why do beams behave the way they do. And then once you understand that, the code requirements themselves start making sense. Once you know the why, the how comes easy. Now, typically in a beam, when you load a beam from the top, it generates forces inside the beam. We call these forces shear and bending. The shear forces will build, as the load bears on the beam, the shear forces will build from the center of the beam and increase toward the reaction. Those are vertical forces that literally shear the fabric of the beam. More importantly than that, though, and what usually governs the design of beams is what we call bending forces, or sometimes you'll hear the term bending moment. And bending forces are the largest at the middle of a beam. Now, if you think about this concept, when you load a beam from the top, you're bending that beam, and in doing so, you're putting compression on the top fiber of the beam and tension on the bottom fiber of the beam. And that's what we see here in this bottom diagram. You can see the red at the top and bottom indicates the tension and compression forces in the top and the bottom of the beam. And then this red portion here at the ends indicates the vertical shear forces in the beam. Now you'll notice that the red indicating the bending, the tension and compression, is a deeper red because those forces are usually what controls the design. Now, as I mentioned here, wood beams are typically governed by bending, and in any wood member, the tension capacity of the wood member is usually less than the compression capacity, and intuitively that makes sense. If I was to push on a beam, it would fail at a certain load. If I was to pull on a beam, it will fail at a lesser load, meaning that the tension is what controls the design. We're going to see some examples later of why that's extremely important. Shear forces are usually not governing, and so in most applications, like at a roof beam, you can actually cut out a portion of the beam, and the beam is still fine, because the shear is not what controls. The maximum force in the beam is not here at the reaction, it's here in the middle. Another thing in the building code that has been in the code for many years is limitations on how much you can cut and notch into beams. And these figures come out of the building code, and you'll notice the code allows you to cut holes and cut notches into wood framing only in certain spots. In other spots, holes and notches are prohibited. So you'll notice here, in the middle of a beam, the code does not allow notching in the middle of the beam. Now, why is that? Well, going right back to our example here, notice where the highest point of stress is on the beam. Middle part of the beam, top and bottom. And so that's exactly why the code is not going to allow you to notch it. Now, if I go back to my beam here, notice how in the center of the beam, the forces are very low in the middle. Well, the code will allow you to drill a hole in the middle of a beam. So understanding how beams behave makes this code make a lot more sense. And in some ways, if you understand beam behavior, you don't really need to even refer to the code. You can look at a beam and say, well, if I see a notch in the top of a beam or a hole too close to the top or bottom of a beam, I know that that doesn't comply because I know that's where the forces are the highest. Same thing for studs, essentially. You'll notice for studs, concepts are pretty much the same. Studs aren't acting like beams, so they don't have a lot of bending. but there are still limitations on how much you can bore into studs. Cantilever beams behave similar to simple span beams, but the main difference is that the maximum forces in the cantilever occur at the support and usually not in the midspan. And it depends. I don't want to generalize too much, but for a cantilever beam with any significant cantilever on it, you're going to find that the forces are probably highest here, although you will still get some high forces here in the midspan. As this cantilever dimension shrinks, the midspan forces might start to control. But understanding this behavior, it becomes clear you shouldn't be seeing any notches here in a cantilever beam. That would be the point of highest stress. Now, going back to, in our first part of our training, we talked about engineered lumber. And one of the primary types of engineered lumber that we see on projects is glue-laminated beams, or Glulam beams. Basically, they're 2x that are glued together to make larger beams. And there's different stresses of glulam. When they glue the different pieces of wood together, not all of those laminations are equal. Some of the laminations are high-grade lumber that can take a lot of tension stress. And those laminations are placed on the outer laminations of the beam in order to give it more strength. So one type of glulam is what we call a V4 glulam. And it has higher stress lumber on the tension side only. Then there's also V8 glulam, which has higher stress lumber on both sides. Why is that important? Well, if you have a simple span beam and you order a V4 glulam, they've provided the higher tension lumber on one side of that beam only, and so you've got to install that beam properly. You'll see the beam will be stamped with a stamp that says top. That's very important that the orientation gets done right, because making sure that the laminations are installed in the proper location. A V8 glulam, you have high stresses, you might have a high tension stress here, and then you have a high tension stress here. And so on cantilever beams, a V8 glulam is ordered, and that provides high stress lumber on both the bottom and the top of the beam. Okay, let's take a look at some of the errors that we've seen in the field here in Santa Clarita. I went ahead and put some photos here that I'd like you to take a look at. Here's an example of an overboard joist. These are floor joists, and you can see that somebody has gone in and bored holes, and you can see the holes are very close to the bottom of those joists. Now, if you're a building inspector or a contractor, and you understand, now that we understand how beams behave, you'd instantly identify this is a big problem. All of the high-stress parts of the wood have been compromised by these holes. So something like this, city building inspector would write up a correction. This needs to be resolved. The fix for something like this would either be to replace the joists or retrofit them with some kind of an engineered design. Here's an example of an overcut beam. You can see here where somebody took a saw, and in order to get these pipes through the beam, they went ahead and just cut right through the bottom of the beam. And to make matters worse, this beam is supporting another beam right here. So right next to the support for this beam, they've gone ahead and compromised the structural integrity. This is a big, a big problem. And again, the solution for this would be some kind of engineered retrofit or just completely replacing the beam. Now you might wonder, when you see, sometimes you go out and you see big errors like this, holes cut in beams and severely compromising the structural integrity. You might ask, well, how come that thing's still standing? Why doesn't it fall down? And one thing to keep in mind is we design structures for dead and live loads. And the live loads that we design for are loads that aren't always there. They might only be there for a short period of time during the life of the structure. So in a situation like this, they're just lucky that the live load isn't there. But make no mistake, we've seen folks do damage like this to their homes and have collapses So cases like this, these are just the cases where we were actually able to go out and take a picture because nothing catastrophic happened. Next example here is you've got somebody went ahead and cut an existing header right here, and they went ahead and framed a new header in, and it doesn't run all the way back to the support. So they went ahead and just put a strap in there, a steel strap. Is that strap capable of transferring any of that vertical shear? No. I mean, this does not comply. Now, luckily, we don't have live load up on the roof, or this might be a collapse hazard. But now that we've talked about the physics of beams, and you understand that at the end of a beam is where you have shear forces, vertical forces, understanding the physics, you understand that a strap like that doesn't do you any good. You know, straps work in tension, not in shear. And so that would not be an acceptable fix for what was done here. Next example, remember we talked just a moment ago about Glulam beams. And this is an example of a Glulam beam that was a V4 Glulam, meaning it had its strongest wood material on the bottom of the beam. And so you're supposed to install it with the top on top and the bottom on the bottom. The fabricator went ahead and indicated what was supposed to be the top of the beam, and our building inspector went out and they had installed the beam upside down. Understanding the behavior of beams and the behavior of materials and knowing why, now you know why this is such a problem. Basically, the strong part of the beam is on the wrong side. So when that beam is loaded, the poorer quality lumber on the bottom is now what's taking the tension. And so this is absolutely not acceptable unless the engineer can prove that the beam was over-designed. Maybe there's a chance the beam was designed with extra capacity and they can go ahead and continue to use this beam. But for the most part, when you see that, that's a huge red flag. That's probably something that is going to either need to be replaced or retrofitted. Okay, still on beams. One thing that's important to note is that all beams, regardless of what purpose they serve in a structure, have to be positively connected to their supports. And this is something that unfortunately we see done wrong a lot. You can see here, the building code requires the beams, even those beams which support only vertical loads, have to be connected to their supporting elements. And there's the code section there that requires that. If there's no lateral force on a beam, you still have to connect it for at least 5% of that vertical load. Okay, so if the beam reaction were 5,000 pounds, the connection must support a load of 250 pounds. Not hard to do. You know, a small post cap or framing clip will do that job. So let's take a look at the photo real quick. Here's a beam that frames in and sits on a post. And you'll notice there's no connection here. It's just sitting there. Now this beam isn't on a shear line, so there isn't any seismic force acting here. But the code still requires that you have to provide at least a minimal connection here, 5% of the building or of the beam's reaction. Okay. All right, so that covers beams. And the reason we start with beams is because the physics of beams, you're going to see this repeated throughout the remainder of this training. Keep in mind the concept of a beam. When you load a beam, it puts bending on it. It creates tension on the bottom and compression on the top. Moving on to diaphragms, and the word diaphragm when we're talking about structures or buildings simply is just a technical word that engineers use to talk about roofs and floor structures. So we talk about a roof diaphragm. Well, the word diaphragm just means we're just talking about the roof, the plywood, or whatever structural element serves as the roof. And of course, let's start with the physics of diaphragms. Diaphragms behave like beams. And so this is a floor in plan, so we're looking down on our structure, and you'll see that the diaphragm spans from one side of the structure to the other. And it's loaded by lateral forces. So the force here that's loading the diaphragm this way, that would be lateral force pushing on a house, wind load, seismic load. So In the same way, when you load a beam, it creates that tension, compression, and shear force. Diaphragms behave the same way. So this force pushing this way is going to put tension here on this side and compression here on this side. And of course, when we talk about seismic loads, the loads reverse. So when the seismic force goes one way, you'll have compression. When the seismic force goes the other way, you have tension. You'll always have reversal of force that you have to consider in your design. Also, like a beam, the shear forces build as you get toward the shear walls. And so those vertical shear forces increase from one end of the structure to the other. Now you can also imagine if you were to bend a beam and there was a portion of the beam cut out, the stresses at that cut would be higher. Same thing with floors and roofs. The stresses at corners are higher, and so we have to design for those. Now, typically in wood frame homes we use plywood or OSB diaphragms, and there's two different types of diaphragms, blocked and unblocked. Blocking just means that there's 2-bys that the diaphragm pieces, the pieces of plywood, are nailed to. Whether those blocks are present or not is whether or not you have an unblocked or blocked diaphragm. Obviously, blocking the diaphragm and adding that nailing gives you a lot more capacity, and we can see that right here. Unblocked diaphragms, you get about 120 to 320 pounds per foot. A blocked diaphragm, you can get capacities all the way up to 820 pounds per foot. In addition to that, the building has something called high-load diaphragms, which have multiple rows of nailing, and you can get even higher forces, although those are not quite as common in residential construction. Now, in a beam, when you bend a beam, it's the fibers in the beam that take that tension and compression force. In a diaphragm, those chord forces, those tension compression forces, are carried by the home's double top plates. So in a stud wall, you have the 2 plates at the top and bottom, or 1 at the bottom and then 2 at the top. That double plate is your what we call your chord, or your tension compression element. And so the building code requires that the top plates in wood frame construction be spliced. Anytime the 2-by at that top plate stops and another one starts, there has to be a tie connecting those two together so that any tension force is transferred from one plate to the next. So now we know why. That tension force that we're transferring are these chord forces here when the load is acting, when the seismic loads are acting. So here's a couple of sort of standard details that I've given you here. Usually those splices are done with nails. Sometimes they're done with steel straps. And then you'll also see when you cut holes in your top plates, you have to make up for those holes by adding straps to the plate. Now, when the diaphragm transfers shear, that shear may be greater in some parts of the house or it may be lesser. Here's an example of a tract home in Santa Clarita, and I thought this was a good example to show exactly how diaphragm works, show a photo so we can really get a feeling for what's going on. So what we have here is, up here, this is a plywood shear wall up on the 2nd floor of our house. This is a plywood shear wall on the 1st floor of our house. And this portion right here is the floor on the second floor framing. So we've got our wood eye joists, and we've got, you can see we've got plywood in here. Okay. Now that we understand the physics, what is that plywood doing? Well, this plywood here is taking the shear from the upper floor and then transferring it to this wall, to the shear wall on the 1st floor. Okay. Now, something interesting to notice here. Because these two walls are offset from each other, there's a lot of shear force being transferred through that plywood. Notice, you see the 2-by blocking? Here, here, here. That's a block diaphragm. Makes sense. If you were in the field and you saw, or you're designing a plan, and you see a shear wall that transfers from one shear wall through the floor to another shear wall, you're expecting that piece of floor to be much stronger. And so in this case, you'd block the diaphragm. You'd add that blocking to give it that extra strength. So with this concludes the training on beams and diaphragms, and also part 2 of our training. We're going to go ahead, and in the next part we're going to move on to part 3, and we're going to revisit some of these concepts and get into, once we get into the actual design globally of our house, you're going to see some of these concepts revisited. And so thank you for listening, and we'll see you back for part 3.